Welcome. Today, we're diving into the world of numbering systems and codes. We'll explore how different systems work, why they matter, and how they shape the way we communicate and process information. Let's get started with Ernesto Gómez Vargas leading the way. Let's talk about the decimal system, also known as base 10. It uses 10 digits 0 through 9 to represent any number. Each digit's position tells us its value, from thousands down to units. For example, the number 4,149 breaks down like this: 4 times 1,000 plus 1 times 100 plus 4 times 10 plus 9 times 1. By combining digits this way, we can build any number we need. Let's explore how numbers are represented in a positional numbering system with base. Each digit's value depends on its position, multiplied by b raised to a power, positive or negative. The base b is an integer greater than 1, and each digit falls between 0 and b minus 1. The dot between digits marks the fractional point. When b is 10, we call it the decimal point. When b is 2, it's the binary point. This system forms the foundation of how we write numbers. Let's look at different numbering systems we use, starting with the decimal system, the one we use every day. It's based on 10 symbols from 0 to 9. Then there's the binary system, which uses just 2 symbols, 0 and 1, called bits. Next, the octal system, based on 8 symbols from 0 to 7. Finally, the hexadecimal system, which has 16 symbols, numbers 0 through 9, and letters A to F. Each system serves a unique purpose in how we represent numbers. Here, we're looking at how to express numbers in any base, which we call base B, and convert them into base 10, the system we're most familiar with. The notation shows digits multiplied by powers of the base, both positive and negative, depending on their position. For example, the number 101.12 in base 2 breaks down into 4 plus 0 plus 1 plus 0.5, which equals 5.5 in base 10. Another example is 4518, which converts to 297 in base 10. This process helps us understand numbers across different bases. Now, let's focus on converting numbers from different bases into base 10. We have a variety of examples here: binary numbers like 10,101 and 0.101, hexadecimal like AC74, octal such as 467, and even a base 4 number, 332,214. The goal is to practice moving from any base, which we'll call base B, into our familiar decimal system. This skill is fundamental for understanding how different numbering systems relate to each other. Let's talk about how to convert a number from base 10 to any other base, like binary, for example. We do this by dividing the number repeatedly by the base we want. Each division gives us a quotient and a remainder. We keep dividing until the quotient is smaller than the base. Then, the digits of the new base number come from the last quotient followed by all the remainders, but in reverse order. The last quotient becomes the most significant digit, and the first remainder is the least significant, on the right. Let's look at how the decimal number 18 translates into binary. In base 10, it's just 18, but in binary, it becomes 10010. This example shows us how to convert from base 10 to base 2, or any other base, really. Understanding this process helps us see how numbers work differently depending on the system we use. It's a key step in grasping how computers handle data behind the scenes. Now, let's put what we've learned into practice with some exercises. We'll start by converting the number 3,245,610 from base 10 into bases 16, 8, 4, and 2. Then, we'll explore how to convert any number from base 10 into a general base. These exercises will help us solidify the concepts of number base conversions and deepen our understanding. Let's look at how to convert a decimal fraction like 0.1875 into its natural binary form. We do this by repeatedly multiplying the fractional part by 2. Each time, we note the whole number part, either 0 or 1, that appears before the decimal point. These whole numbers, collected in order, form the binary equivalent. So, for 0.1875, this process gives us 0.0011 in binary. It's a straightforward method that turns fractions into binary step by step. Let's break down how to convert a decimal number with a fractional part into binary. We start by separating the whole number from the fraction. For the whole part, we divide by 2 repeatedly, knotting the remainders. That gives us the binary digits from right to left. For the fractional part, we multiply by 2, extracting the integer part each time to build the binary fraction. This step-by-step process transforms a decimal like 27.42 into its binary equivalent, combining both parts seamlessly. Here, we see how numbers look across different bases, from the familiar base 10 to binary, quaternary, octal, and hexadecimal. Each column shows the same value, just expressed in a different system. Notice how binary uses only zeros and ones, while hexadecimal goes up to the letter F to represent values beyond 9. This table helps us understand how computers and digital systems represent numbers in ways that are efficient for their design. It's a key step in decoding how data really works behind the scenes. Here, we see how binary numbers translate into other bases that are powers of 2, like base 4, base 8, and base 16. Each group of binary digits corresponds to a single digit in these larger bases. For example, 2 binary digits make 1 base 4 digit, 3 make 1 base 8 digit, and 4 make 1 base 16 digit. This system lets us represent large binary numbers more compactly and readably, which is crucial in computing and digital electronics. Let's look at some examples of converting between number bases that are powers of 2. First, converting A5116 to base 2. We use the binary equivalents for each digit. A is 1010, 5 is 101, and 1 is 1. Putting those together, we get 101,001,010,001 in base 2. Next, converting 111,110,100,100,111 in base 2 to base 16. We group the digits in sets of 4, from right to left: 1111, 1010, and 111. Each group corresponds to a hex digit, F, A, and 7. So the answer is Fa7 in base 16. For base 8, we group in 3s, and for base 4 in 2s. This works because these bases are powers of 2, making the conversions straightforward. As we wrap up, this table shows how the same number can look very different across various bases, from binary and quaternary to octal, decimal, and hexadecimal. It's a clear reminder of the flexibility and power of number systems. Now, it's your turn to practice and explore these concepts further with the exercises. This video was created with SlideSpeak. Visit SlideSpeak to turn your presentations into engaging AI-narrated videos.